Shall we start? I can hear. Good afternoon, everyone. Glad to host today's seminar presenting by the USFB Students Chapter. It's my great pleasure to introduce our speaker, Professor Matsagar, a global recognized authority from Indian Institution Technology Delhi. His experts expand multiple areas of engineering and his have remarkable contributions to our fire fields as well. Today, Professor Matsagar will presenting to us on the important topic of the service life multiple hazard risk assessment of the structures from fire scenarios. So let's give a warm welcome to Professor Matsagar.
Thank you very much. Thank you for the invitation. And greetings of the day, because I can see that there are participants from some other parts of the world, which are different time zones. So thank you for attending. Today I'll be talking a little bit about service line scenarios. But before I do that, I will quickly give background of where I'm coming from. Because of the budget incompatibility, there are some issues with the layout. Nevertheless, I'm from the Department of Civil Engineering at Indian Institute of Technology, IIT Delhi. In our civil engineering department, we have about 43 faculty members and more than 1,000 students. Our QS1 ranking in the world, it is within 51 to 100, and in India, it is generally first or second. In our department, we have 11 faculty members, 3 chair professors, 1 LFS professors, and in structural engineering, we have total of 3 programs, 2 funded by the government of India and 1 funded by the industry. Shall I continue myself?
Yeah. It's lecture rooms.
Yeah. I hope the audience is audible. I hope the audience is able to hear me. If there are any issues, kindly put it in the chat box. There is poor audio. So this is regarding Department of Civil Engineering and Structural Engineering within that. We are one of the largest department in the system, as well as in structural engineering, we are one of the larger groups. So these are photographs of group meeting. This is the department how to spend. There are different blocks there. Our short-term vision, civil engineering, and then to develop new courses for undergraduate and postgraduate courses, and actively contribute towards the national development of infrastructure. In collaboration with the industries and how to contribute towards the development of building codes. We also focus on the international collaborations and attract internationals to work with us in different capacities as students.
We just try one more time.
Yeah, let's see how it works now.
Oh, it's not better.
Yeah. And in addition to attracting foreign nationals as students, researchers, and faculty members, we are in the process of development of our laboratory infrastructure for conducting high-end research. We are right now working towards development of 3D printing of concrete in construction, real-time dynamic testing of structures using 6D degree of freedom check table, and high quality testing machines for concrete and reinforced concrete structures, materials and structures. As we go along in our long-term vision, we would like to see some centers of excellence in different areas such as earthquake engineering, construction materials, technology and management, and then develop cutting-edge research facilities at IIT Delhi so that we upscale our department to top 20 in the world. That is our long-term vision. And then also focus on the teaching, improving the pedagogy, and as well as taking our research to real scale from TRL, low TRL levels of 2 to 3 to high TRL levels of 8 to 9. Our institute was established in 1961, and you can see that structural engineers have contributed in the development of the institute. What you see here is our convocation hall where degrees are awarded every year, and it is made of reinforced concrete, hyperbolic paraboloid shell structure. And since then, we have been contributing to the development of the institute. Recently, there are some investigations being carried out in different areas in structural engineering, with some books published as well as some patents filed. And we are also transferring our knowledge from the laboratory to the field practice. You see here on this slide some of the contributions that we have made in the national development in terms of development of flyovers, bridges, as well as blast resistance structures and similar contributions in infrastructure development of the country. With that little background of the institute that I am coming from, I would now develop upon the topic of today's presentation, which UQ5 SFPE, the Society for Fire Protection Engineers, the student chapter, they have hosted. I'm very grateful to them. Also, I'm grateful to the University of Queensland faculty member Professor David Na for hosting me during this period of my visit to UQ. Today, my talk will be on service life multi-hazard risk assessment of structures from fire exposure scenarios. And the overall outline of this topic would be, I will talk about some background details of the both the current infrastructure development happening across the world and where it should be going towards in order to make sure that it is sustainable and it is climate friendly. Today, I will not spend any time on reviewing the literature, but during my talk, I will showcase as to what is the current development in the area of multi-hazard resilience of infrastructure. I will also talk about some of the laboratory facilities that we have developed at IIT Delhi and current research works at IIT Delhi, and what are the future works. So there will be some different dots and that I will connect, and I will present what is the current status of development of multi-hazard resilient built infrastructure in the Indian context in particular. Obviously, mankind requires different kinds of structures, be it the nationally important structures, airports for transportation, hospital buildings for our healthcare, as well as for power generation, nuclear power plants and wind turbine towers. For hydroelectric power generation, we need dams, and there are a large number of engineered structures or built infrastructure that we have to develop, and we cannot live with them. That is one of our basic needs. But at the same time, if we have a look at what kind of structures we have been building, these are the conventional practices. We started from stone masonry structures, then brick masonry, and gradually we moved towards the reinforced concrete structures, and these days steel and other composite structures. And then we have to worry about as to how they are performing when they are put to use in the service life of about 100 years. And we see that there are certain issues that most of the developing and developed countries are facing. They are in terms of both environmental impact as well as performance and aging. Old infrastructure has already aged, before they attain their total design life. Typically, for buildings and bridges, a design life of 100 years is considered, but much before that, they have started seeing much deterioration, to the extent that some of them are not even in a position to rehabilitate or retrofit or strengthen them to the extent that they will be usable. So there is no other option than demolishing them and building new one, and that contributes significantly to carbon footprint. There is already significant carbon footprint, as we can see from the construction industry and building sector. I will still keep apart the transportation sector as such. But you can see here there is almost 40% of carbon footprint coming from buildings and construction industry, as high as that. And if you see the energy consumption also, buildings and construction industry contribute significantly towards the consumption of global energy sector. And this is something that we really need to worry extensively about, that how we can bring this down by developing new materials and use them in our infrastructure development. If you see a global picture as to how the building sector energy carbon intensities are, it is again a worrisome picture that we have. If you focus again these two countries, India and Australia, unfortunately, there is a heavy carbon footprint in terms of terajoules, more than 150 tons, and there is a long way to go for us to develop some new building materials and make sure that they are durable, as well as they are resilient to whatever loads that they are going to experience during their service life. And at the same time, reduce the carbon intensive materials in their use in the structural development, and have some alternatives which are much more climate friendly and environmental friendly. So some of these issues we have started addressing at IIT Delhi. We are working towards developing some new materials, and they are more sustainable, they are more nature friendly or environment friendly. There are some local issues also that we face in the national capital of India, Delhi. Surrounding our region, there are farmlands, and during the harvest, immediately after the harvesting season, for preparing the fields, the agro residues are burned, and this is called stubble burning. The agro stubbles, they are burned, and they significantly contributes towards the air pollution in the national capital as well as surrounding area. And it goes almost to the hazardous level, and we need to find some solution to that. So incidentally, at Delhi, in our laboratory, some of our students, they are working on converting these agro residues into some useful civil construction engineering products, such as biocomposites. So currently there is one startup which has been initiated by one of the students on converting these agro residues into biocomposites on the field itself, so that even the transportation costs are also reduced down. Our overall aim is to achieve some kind of circular economy, wherein we make sure that the entire agro residues or the agriculture waste is useful either in the construction industry or otherwise, at the same time making sure that it doesn't contribute to the air pollution and health issues that are caused because of that. If you see our recent projects, I have only listed 3 recent projects here, and all 3 of them are incidentally on development of some technology in terms of making the biocomposites from agro residues, and seeing as to how they perform under some of the extreme loading conditions, and fire being one of the major ones out of that. So with this background as to how new construction materials are required to be developed and used, obviously the next question comes when we build some structure out of it, how that structure would perform, because we have good experience of reinforced concrete, we have good experience of steel, but for us, biocomposites, particularly obtained from agro residues, they are absolutely new material. There are different alternatives available from the agriculture side in terms of converting them into some useful product. If we see here, there are some conventional Conventional organic natural fibers are shown, extracted from sea silk, coir, jute, wheat straw, rice husk, coconut husk, and so on. And we are trying to use these natural fibers in civil engineering construction in different ways and in different forms. And there are several experimental as well as numerical and analytical research projects ongoing in our lab at IIT Delhi. Some of these are already well established, some of them are significantly new. So we started with, first of all, the conventional reinforcement for concrete structures, replacing the steel by introducing bamboo curves. So you can see here there is one representative panel of about 0.7 meter by 0.7 meter. And we have tried different ways how we can reinforce it, of course, to take care of the tensile stresses. And then the subsequent objective was how it performs under exposure to fire. So again, there are two different categories of tests we had to conduct. But then the first question came as to what should be the loading protocol and support condition or the load setup that we should have. Currently, though we have used some way of heating these slabs and then cooling it down to room temperature and then testing them separately under the mechanical load. This is a test protocol that we thought we can go ahead with. However, yet in future, we need to develop some test protocols for testing these kind of new materials and the structures made out of it. And here we had initially applied the load sequentially, means initially it was exposed to thermal load, and then it was cooled down to room temperature with natural cooling, and then exposed to and then subjected to mechanical loading. But then subsequently, we have also tested them with simultaneous application of thermal and mechanical load. And as you can see, with different temperatures, there is significant degradation seen, particularly in the bamboo reinforcement. And at about 400 degrees Celsius, it almost loses its capacity. And you can see there is falling, there is debonding between the bamboo columns and the mortar or fine concrete that we have used. With the increasing temperature, there is significant reduction in the capacity of the bancrete panel. We have coined this word as bamboo plus concrete as bancrete panel. And now we are applying this thermomechanical loading simultaneously. As you can see, this is about 1 meter cube fire furnace in which we can raise the temperature up to about 1300 degrees Celsius. Nevertheless, for this kind of natural fiber specimen, hardly up to 500 to 600 degrees Celsius is sufficient enough. You can see from the top, we insert a loading actuator arm and from this one, and we have an option of providing it at whatever location that we would like to. We decide as to when that loading has to start and what should be the time temperature curve. We are able to achieve the ISO or E119 curve in this. And then there is a stagnation period for some time so that there is uniform distribution of temperature across the specimen. You can see all the thermocouples, K-type of thermocouples attached at the top and bottom, as well as there are other thermocouples to see what is the chamber temperature. Once it is uniform, then we start conducting the test. And once it reaches the uniform temperature, then we apply the mechanical load and measure as to what is the load deflection. So this is one ongoing investigation. Apart from that, there are other natural fibers which are being used either as internal reinforcement, as you can see in the cross section here. They are bonded with this is as well as we have tried with some post tensioning, as you can see in the cross section on the left hand side. Yeah, that's if they are able to see. Yeah, they may not be able to see. That's okay. Yeah. So there are different ways that we would like to use these natural fiber reinforcement in the concrete structures, either bonding them externally or internally. Again, internally with bond or without bond means for example, post tensioning. We have conducted some tests using post tensioning as well, and then to replace the conventional steel reinforcement. So this is again some ongoing work, and in future we would like to see in the common form of concrete structures where they can be placed in conjunction with some other fibers. So we are going ahead with hybridization of the fibers as well as functional grading of these biocomposites used in conjunction with concrete. Of course, one would wonder that we are only looking after steel as a carbon intensive material to be replaced by natural fibers. But though it is not part of today's talk, we are also looking for alternatives to the binding materials like cement, because it also contributes significantly to the carbon emission, the greenhouse gases, as well as higher carbon footprint. I will restrict my discussion today only to the reinforcement part though, and how these structures are tested against some extreme loading. We are collaborating with different schools, including, of course, UQ. This is the collaboration with University of Dundee in UK, where we are trying some other kinds of fibers which are available locally there, rosin fiber, and we are again trying to use them in reinforced concrete structures in order to see how they can be used for replacing the conventional steel reinforcements. There are several challenges in this, of course, and as we go along, we are trying to overcome those challenges. One of the major challenges, of course, what is the bond behavior between the biocomposites and the concrete that we are using it in. But if you see the biocomposite itself, it is consisting of the fibers and some polymer matrix or epoxy, and the combined becomes a biocomposite. Now, if you individually test the fibers and polymer, you will see that the fibers, they are quite brittle, and matrix is relatively ductile, but the composite then becomes a brittle one, because it is mainly the combined failure governed mainly by the fibers that governs the response, and thereby the composites are inherently brittle. And therefore, in order to achieve ductility, we are again trying to develop some new design methods to ensure that there is a higher ductility achieved by using these kind of biocomposites, not through the material route, but through the system route, in the form of sequential failure of different materials put inside these bio-reinforced or natural fiber reinforced concrete structures. Again, their behavior to elevated temperature is not known, and some of our students are working on that. The bond behavior between the surrounding concrete and these kind of different kinds of reinforcement in the structure is also not known, and some other researchers are working on development of some constitutive relations as well as these bonding properties between the two. So this is more from the side of material development and replacing the carbon intensive materials in construction by using the natural products as much as possible. But on the other hand side, when we come to design of structures, we need to also worry about what kind of loading that the structure experience during its service life. So we categorize them into two types of hazards: natural and accidental. Though on the lighter vein, it is said that all the hazards are actually man-made, because even the structures, when they are subjected to a natural event such as earthquake, it is the structure that fails, and the structure is built by mankind, and therefore it is a man-made hazard. So earthquake hazard is also man-made hazard in that sense. Nevertheless, the origin of these events, either they are from the natural part or they are completely accidental or man-made in the industry. So there are different loadings that also we worry about. So conventionally we have loads and load combinations, but what we are proposing now, since we are working in this area, is that is not enough. We cannot just restrict ourselves to loads and load combinations. We have to go beyond that, and we have to worry about the multi-hazard risk assessment of structures, as well as it is not just at the construction stage or at the design stage. It should be also looked into during the service life stage as to how the structure performs based on what kind of scenarios that the structure is going to experience. Obviously, not every structure is subjected to all these kind of loading possibilities. However, we have to see for a given structure what kind of load it would be subjected to. There are several sources of loading. There are different hazards, and one can go on and on in looking after this. However, we have to see for a given structure which out of them are relevant and what is their time of occurrence, what their intensities are, and so on. But the bottom line here is that mere load and load combinations are definitely not adequate. For some strategically important structures, whereas blast is important, for some other structures located in earthquake prone area, earthquake becomes a major hazard. Likewise, the use of the structure also governs as to how its response or how its performance should be. For example, for healthcare, the vulnerability of health sector infrastructure should be much less as compared to some unimportant storage kind of structures. So vulnerability assessment of structures depending on its use and depending on the exposure condition, depending on what kind of intensity it will be exposed to, we need to evaluate the vulnerability, and eventually we go to quantifying the risk associated with it, not only at the design and construction stage, but also during the service life of the structure. And this is one area where almost no work has been done, unfortunately. And if you go through the literature, you will find hardly any contribution being made as to how to take care of this service life based multi-hazard risk assessment and design the structure to fulfill certain performance requirements. Even I will talk about it later, that performance based engineering is taking its roots in mainly in earthquake engineering, but other disciplines it is yet to completely be developed. If we see the global scenario of occurrence of these different hazards, you will see that particularly in the Indian Peninsula, there are several kinds of hazards happening. The diameter of the circle shows the intensity of that hazard, and the colors, if you can see on the right hand side, there is a palette. There are geophysical events, meteorological events, hydrological events, climatological events, and you can see particularly in the Himalayan belt, there are significant earthquake activities, which is categorized under the geophysical events. And if you see the shoreline area of India, you can see that there are significant number of meteorological and hydrological event, which consists of the flood, which consists of the storms in those areas, as well as there are some areas which are exposed to heat waves, which are climatological events. So in nutshell, India is a country that is exposed to multiple hazards. Even if we see on the eastern side, China is also subjected to number of these kind of multiple hazards, but more typically the meteorological events such as the storm events. If you see in the Australia, again, winter storm is one of the worrisome part. And the other day when I was talking to one of the faculty members in University of Melbourne, I was told that flood hazard is one of the major concern in some of the areas in Australia. So in nutshell, there are a number of these events that keep on happening, and we need to worry about a design of our structures against that. Otherwise, definitely it is going to cause both in terms of fatalities and in terms of economic loss. So if you see on the first column, the first bar chart, the overall losses in terms of US dollar billion are shown. Japan and Europe, they are significantly affected because of these hazards in terms of economic losses and insured losses. But if you see on the right hand side, the third column, India is ranked second after Ecuador in terms of fatalities. So if you see on the first two columns in the first two bar chart, India is not seen, or even Pakistan or Afghanistan, they are not seen. But on the right hand side, they are all figuring. What it means is the number of fatalities in these countries are higher, even when the number of such events are relatively low. So if you study this report of reinsurance company in Munich, you will observe that most of the underdeveloped and developed countries, even when they are experiencing less number of hazards, the number of fatalities are higher, whereas mostly the so-called developed countries, though they do experience number of hazards, and because of that there are overall economic losses, the number of fatalities are lower. Of course, our objective is to save life, and therefore we need to reduce the number of fatalities. So there is no doubt that we need to worry about the multi-hazard analysis and design of the structure. But if we have a look at historically what has happened, so the first historic record of multiple hazard means one hazard following the other, like earthquake following fire followed after an earthquake. The 1906 San Francisco earthquake is the unfortunate example of this. So during this San Francisco 1906 earthquake, because of the earthquake, there were hardly any fatalities or any damage caused, because in that part of the world, in the west coast of US, because of the significant earthquake activity, most of the structures are built earthquake resistant, and therefore earthquake did not cause any damage as such. But a fire was triggered, and that spread almost in half of San Francisco city, and it turned into ashes because, of course, they were not ready for it. So it was one of the very unfortunate incident that has happened because of the cascading event of earthquake followed by a fire event. So more than 3,000 people died, and almost 80% of San Francisco city was destroyed at that time. And if we see in today's, it's in 2050, it is $6.2 billion of economic losses. So this is a very peculiar example of multiple hazards, but there are several others. Though it has happened in 1906, subsequently in 1994, almost about 90 years after that, we have probably not learned the lesson. And again, in Northridge earthquake in 1994, some of the structures have caught into fire, and again there were significant economic damage, though the casualties were not as high. It was about 87 people who lost their life during these unfortunate incidents. But of late, probably most of us have experienced this unfortunate incident of Fukushima Daiichi nuclear disaster in 2011. Again, this is a very peculiar example of multiple hazards. There was first a tsunami. Obviously, we understand that tsunami is triggered by an earthquake. In this case, it was the Great Japan earthquake, excuse me, of magnitude 9. And in this case, it led to, unfortunately, the nuclear hazard, and that eventually given rise to the health hazard. And in this case also, though the death toll was not as high, the insured losses were $235 billion of US dollar as estimated. So with this background, at IIT Delhi, in our multi-hazard protective structures lab, we have been working on multi-hazard resilient infrastructure. And out of all these different possible hazards, we have taken those which are most common, two from the natural hazards. They are earthquake, ground motions, and wind loading on the structure. And from the accidental hazards, we have taken two. And those are blast-induced, accidental blast-induced forces, either in terms of ground motion or in terms of the pressures, and the fire loading, either accidental or otherwise. So we have these four hazards that we have started working on, and to see as to how the structures perform under the action of these different events. But as I said in the beginning, we need to define the scenarios, and for a given structure, what kind of scenario of this loading would happen, that we look into, and then we analyze it. So that scenario definition becomes quite important. And then there are different construction materials also that we use, the conventional ones such as masonry, and then the contemporary steel and concrete and their composites, and the advanced engineered materials such as fiber reinforced polymers. All of them needs to be evaluated at both structure level and system level to quantify their performance, and then to see as to whether we are able to achieve the desired performance or not, both on the deterministic scale and the probabilistic scale. under the different kinds of loading that it is going to experience. And unfortunately, there is an interaction between these events, and I will quickly talk about what that interaction is in the subsequent slide. So eventually, we work at two levels: material level and structure level. At material level, in order to quantify their physical, mechanical characteristics, and then at structures level to see their structural performance in different terms. And in terms of scenario definition, incidentally, I had an opportunity to serve as a member for the National Building Code of India, developed by Bureau of Indian Standards, and there one chapter is completely devoted to multi-hazard analysis and design of structures, wherein in one of the maps we have shown as to what kind of hazards that Indian peninsula or a country is exposed to, and based on that we can define the scenario as to where the structure is located, the intended new structure is to be built, and what kind of load it would be subjected to, and what would be its frequency and intensity. So if you see on the right hand side, in most cases we worry about a single hazard happening and load combinations, but that's not enough, because there are at least two hazards happening over 4 million kilometers square of land cover, and more than 800 million people are affected because of that. And that's where the multi-hazard loading scenario is required to be worried about. Now, if we start from the multi characterization, again, the conventional ways might not be sufficient. We need to see as to what kind of testing equipment or setup and load protocols we need to develop. What you see here is one of the facilities that is developed for characterizing material at different temperatures, where you can see a fire furnace attached to some thermocouple. Again, it can reach up to about 1380 degrees Celsius, and it is fitted within a universal testing machine, and the load is transferred inside the specimen, and then we test different kinds of materials in there to develop the constitutive relation, so that we can use them for analyzing and designing against a given load, in this case the temperature load. But this is only one scenario definition as to how the loads are being acted on the structure, such as it is temperature and mechanical loading. However, for earthquake, for wind, and for blast loading, we need to come up with some kind of test facilities as such. If we talk about the probability-based approaches, the foremost requirement in this case is what is the hazard definition. We need to define the hazard, then its intensity, and when we try to quantify its vulnerability, we need to understand what are the important intensity measures we have to choose in order to finally reach towards the fragility analysis, which will again give us an idea about the different performance level, and then give us an idea about what kind of risks are associated and whether we are okay with it or not. So we use these terms when we go towards the performance-based analysis. Conventionally, we used to only worry about the static loads, but now we are also more worried about the dynamic load, particularly because the structures are becoming more and more flexible. Structures are becoming more and more taller, and because of that, on one hand side, we have change in the stiffness of the structure, which also means there is change in the frequency content of this structure and its response. And on the other hand side, we have started using newer and newer types of engineered materials. So this is from the structural viewpoint, but from user viewpoint also there are significant changes happening. Users are more now worried about the serviceability, and therefore performance requirements from user side also have increased, and therefore the conventional design approaches may not necessarily suffice analysis and design of structure. Therefore, whatever risks that we are calculating, we need to be very cautious about whether those quantification of the risks are appropriate for a given scenario or not. So there are different multi-hazard scenarios that exist. However, we categorize them into three parts: those which are acting or happening independently, those which are following one after the other, and those which are happening simultaneously. So if you see the probability of that multi-hazard, we have only about two events, event A and event B. So when they are happening at different times, they are not correlated, but there is one structure through which we need to be careful about the assessment of the structure. So these are the A and B. For example, at some time there was an earthquake, and after a few years, a few months, there is another event, either in terms of windstorm or flood. So we calculate the response of the structure as to how it performed during that earthquake, and because of the damage caused because of that earthquake, how it is now performing against, say, for example, wind hazards. But these two hazards, they are completely independent of one another. If you see the second category, it is the conditional probability of event B happening, event A. So event A triggers the second event, and the example that we have just now talked about, the San Francisco 1906 earthquake followed by fire event. So because of the earthquake, there is some damage incurred in the structure, and followed by that there was a fire incident. So that fire incident was triggered by some intensity level of earthquake. So this is another example of fire following earthquake, which we have studied, and I will talk about it a little bit. And then the third category is these events are happening simultaneously. So event A, event B, event C, and so on, they are happening simultaneously. And the peculiar example of this is the storms followed by heavy rains, and that is again followed by flooding. For example, in case of Hurricane Matthew in 2016, first there were heavy winds, it was followed by storm surge and then flood, and subsequently after that, at some places there were fire incidences as well. So there were different events happened during this 2016 hurricane in Florida. And there were more than 1,650 fatalities in that event, and insured losses are more than $10 million. So still, even in today's day, these kind of multiple hazards, they are causing a lot of devastation, not only in terms of insured losses, but also in terms of loss of life, which is worrisome for us. And therefore, we need to have some scenario-based multi-hazard resilient infrastructure done. If you see the industrial infrastructure also, this is an example of a factory in Mumbai. There was an explosion first, and it was followed by a fire event. And after that fire event, you can see there is almost complete destruction of the entire facility. And again, at the design stage, I will wonder if anybody has considered this as a possibility. So there are a number of challenges in the multi-hazard risk assessment, and the challenges are: what are the different scenarios that are possible, how they interact with each other, and there is no information available in terms of what intensity it has happened and the timeline that it has happened and what kind of failures have happened. And still, we are required to design our structures for these kind of events. In this particular fire following blast event, there were 47 people died and more than 200 injured. And again, for our industrial infrastructure, we need to design the structures which might be subjected to a fire following a blast event. I think I can take 10-15 minutes. Yeah. So conventionally, when we talk about one hazard, calculating or evaluating the vulnerability is relatively straightforward. You have only one intensity, and then you see what is the probability of failure against that one intensity of loading level. But if it comes to multi-hazard, then the response surfaces in terms of, say, for example, in two hazard case, you have intensity measures of two different hazards, and then find out as to what is the fragility surfaces that can be estimated even from the response surfaces. Now, if it is more than two hazards, then we have to plot them on different scales and see as to how they are interacting with each other and find out as to how vulnerable they are. And then whatever technological interventions that you are doing in terms of any control, in terms of some material which is resilient against some given hazards, how we are lowering down the probability of failure on these different scales or on these different intensity measures. So in order to do that, because it is on stochastic scale, probability scale, you need significant amount of data. We need to also define the limit states of failure, and then we need to, of course, decide what is the intensity that plays a significant role in quantifying the vulnerability of the structure. I have taken only two examples from this for today's talk because it is related to mainly fire exposure scenarios, and there are two fire exposure scenarios that I will quickly talk about. One is the post-blast fire scenario, and the second is post-earthquake fires. First one is the the fire exposure after the blast, the post-blast fire scenario. So we have developed an analysis framework under the event of exposure of a reinforced concrete panel subjected to first a blast event and followed by that a compartment fire from inside. So we actually calculated what are the blast loads acting for a given real life situation. Obviously, you can imagine the pressures are gradually reducing toward the top. Again, depends on what is the standoff distance and what is the quantity of explosive exploded. And then there could be a trigger of fire either from inside or outside. We have taken one example as such for the sake of understanding, and then develop this framework as to if we develop high fidelity numerical model, a detailed finite 3D finite element analysis having all nonlinear properties of steel and concrete taken into account and model, and then variation in these properties both in terms of material as well as loading, and then checking as to when these two events have happened one after the other, whether the failure has occurred or not. And then we try to change the intensity measures and see as to what kind of failure curves that we are obtaining. So this is one simple loop that one can understand how to obtain the fragility curves for one event following the other. Of course, we have also independently obtained them, and then we have found that when they are happening one after the other, means fire followed by a blast event, the probability of failure has increased as compared to when these two events are happening independently. If you see the response also, overall, what we worry about in fire engineering and mostly for health infrastructure is, or healthcare infrastructure is, that what is the fire rating that we get. And again, we have found that there is reduction in the fire rating when these two events are followed by each other. Typically, at least if I talk about IIT Delhi campus, there are some incidences of fire we have seen, and those incidences of fire happen after some uninterrupted power supply, UPS, has exploded. So there was some minor damage because of that explosion, but then that triggered the fire, and there was major fire erupted in some of our laboratories. So those events can be modeled using this kind of multi-hazard analysis framework for fire following blast. Post-earthquake fire scenario is rather common as compared to the earlier one. There have been number of incidences of post-earthquake fire, and the losses, as you can see, there is a huge number of casualties or fatalities in terms of loss of human life. Even if you see even the latest one, also we are seeing that this fire following an earthquake is quite significant hazard that we need to worry about. So with collaboration at UQ, we are trying to work on this problem, which we have been continuing to work since past several years now. We are developing high fidelity 3D finite element numerical models to accurately model the reinforced concrete structures with longitudinal and transverse reinforcement and different fire compartment fire exposures such as one-side exposure, three-side exposure, or all four-side exposures, and with different time temperature and material properties. So both on metal side and loading side as well as on the structural side, we are trying to go towards as accurate modeling as possible. And that is also happening at both the deterministic scale as well as on the probabilistic scale. Here on the top is for a reinforced concrete portal frame. When it is subjected to only earthquakes, what kind of damage have incurred, when it is subjected to fire followed by the earthquake, what kind of damage have incurred in those reinforced concrete members, and depending on what is the intensity of the earthquake that has hit the portal frame, then how much damage has incurred, and subsequently what has happened to the fire behavior or fire response of the structure. So when we plotted the fragility surfaces in this case, we have taken two intensity measures, fire load density on one axis and P ground acceleration on the other axis, and then evaluated the probability of failure. Naturally, if you see the undamaged cases for the exposure to fire, the probability density is higher as compared to when they are subjected to some kind of an earthquake, 0.8 G of earthquake. There is significant reduction in their capacity to resist the fire loading, as well as there is larger deformations occurring in the members. As you can see in the top figure, we have mentioned as to at what location we have measured these deformations. Obviously, this tells us that because of the damage incurred in the reinforced concrete member, because of that earthquake, there is reduction in its fire resistance capacity. However, again, quantification of this damage for an earthquake is relatively straightforward, but the damage quantification also needs to be done on the service life basis. So again, Akshay, who is sitting here, he has worked on quantifying the damage caused because of some different factors. Two of them are much prominent: carbonation in concrete and chloride-induced corrosion in steel reinforcement bars. What kind of damage it causes to the reinforced concrete structure, depending on what age it is. So he has considered 100 years of service life, and what happens to the grade of concrete, modulus of the concrete, which has direct effect on the serviceability in terms of deflection and vibration, and what happens to the reinforcement and how it degrades, and if we introduce certain strengthening measures, what level we can reach up to and what will be the factor of safety. So this is an ongoing work in collaboration with UQ to see what are the effects of the different agents that work on the structure and how they degrade the material properties, and whether or not we are satisfied with the factor of safety that are left. So he has developed this assessment framework for these kind of structures. So there are different boxes, as you can see. First is the hazard definition, as I said, one of the most important one, which also defines the scenario. What are the different kinds of hazards that needs to be taken into account, and what are their timelines. And the next one is the structural analysis. Again, we typically tend to or prefer to use the high fidelity finite element 3D finite element models. Again, depends on what is the time constraints or computational time requirements. So in this case, we had to come down to the framed model rather than 3D, but for other cases we have used the 3D finite element. And then how it affects the decision making for the structure, and it also incorporates the strengthening measure, as you can see the red color one, and this we carry out for total 100 years of the structure as to what happens when there are certain earthquake events taking place to its fire response over the period if there is some eruption of the fire. So these are the kind of analysis framework that we need to develop for different kinds of hazards that a structure receives, and then see as to how these new materials, when they are characterized at a particular level, how they are performing. And there will be some surprises for us. For example, in case of a portal frame subjected to fire, we have seen that its behavior is significantly different even with just small change in the boundary conditions, for example, obviously because of the change in the exposure condition, what kind of loading it has, but we have seen that there is significantly different system or structural level response that in case of this portal frame, which otherwise is not so intuitive. This work is further being carried out with non-simultaneous or non-cascading occurrence of earthquake and fire. again on the probabilistic scale, but here one of the challenges is how to define even the intensity measure, which out of the intensity measure to be taken. Earlier we have simply taken the Q in the fire load density on the x-axis, but here we are first of all working as to which kind of intensity measure is more suitable for development of this kind of analysis frame. So I'm coming towards the concluding or bringing this whole thing together. So in this flow chart, this box is our traditional analysis and design of structures. What we would like to do is we would like to complement it with an additional analysis box, and that relates to the multiple hazards. So as I have said, that definitions of the multiple hazards is important, then scenario specific and site specific hazard definitions are required, and those probabilistic models are required. What happens to the material properties during the service life is important. Once you take that into account, whatever analysis models that I have shown you, they are incorporated in there, and they give back as to what is the performance of the structure. If that performance of the structure is acceptable, if that factor of safety is acceptable, we complete the design, but otherwise we go back and go through that iteration of carrying out the design optimization. But here again, when we talk about whether it is satisfactory or not, we again would like to do that on a performance-based scale, and that performance scale is not fully developed except in earthquake engineering. So that gives us a new challenge as to how to evaluate performance-based evaluation of the structure when it is subjected to the multiple hazards. So we have introduced this new multi-hazard assessment, and now the current work is how to first of all take it towards the vulnerability assessment, and then eventually translate it into performance-based structural design, taking into account the service life performance. So hazard definition, as I have said, then the service life, the duration of the structure that it would be serving, how the material properties are degrading, and how they will change in the response of the structure. All this requires huge amount of data. So essentially, we are currently focusing on service life risk-based structural design method, designs of structures according to the risk in terms of failure and or economy associated with the structure against multiple hazardous scenario throughout the service life of the structure. So these are the ongoing investigations. If you put it in a perspective as to where we in structural engineering have started from. So long time back, we were working just on working stress method, as you know, but subsequently ultimate load method was introduced for a very short duration, but it was replaced by limit state method, and now across the world we are following limit state. But later on, performance-based engineering has seen its day, and since last about 2 to 3 decades, we have been working on performance-based engineering and risk-based structural design. But now, if I see in future, we will probably go towards multi-hazard risk-based structural design and service life risk-based structural design. Particularly in today's discussion, what is important is even for the performance-based engineering, we need to have those kind of frameworks developed or analysis approaches developed for performance-based engineering, which are yet to be fully developed as compared to what it is there for earthquake engineering. Particularly from the performance-based structural fire engineering, I foresee there are a significant amount of opportunities for collaboration because much work is required to be done in performance-based structural fire engineering in terms of modeling, in terms of developing the material properties, constitutive relations, how they interact with each other during the response evaluation. All that is currently an ongoing activity. So these are some of the takeaways from my today's presentation. The code-based structural design methodologies are still prescriptive in nature, and thus they provide lesser importance to the specific scenarios that I have talked about. Performance-based engineering does take into account the elastic behavior of the structure for site-specific condition. And in future, risk-based structural design will be introduced, and it will take into account the risk in different forms, either economic risk or loss of life, risk of loss of life due to certain scenario-based and site-specific hazards, and more realistic assessment of the structures based on multiple hazards will be taken into account in the future building codes. Already some work is ongoing where again, I happen to be one of the committee members working on the multi-hazard analysis and design of the structure. And down the line, probably the building codes, national codes will change from the currently design stage based and construction based approaches to the service life based approaches for the design of the structure. I summarize this in pictorially also. So our conventional structural analysis design is based on just initial factor of safety. However, if we incorporate these multiple hazards and what happens to the certain properties during the service life of the structure, what are the different possible scenarios, then we change that conventional analysis and design strategies into multi-hazard structural analysis and design, where we do take into account the site-specific and scenario-based consideration to make sure that we have got a factor of safety, which is acceptable factor of safety for a given structure under given conditions throughout its service life. So with that, I conclude this presentation, but I would like to thank the invitation that I have received from Professor Lal as well as from the student community here for delivering this presentation, and I'll be glad if there are any questions or there are any comments or there are any points of discussion on whatever I have presented. Thank you so much for your attention.
Thanks very much, Vasant Matsagar. So we start from, is there any question from I?
There are some chat messages.
That's from Progressive.
Okay. All right. Yeah, sure.
And is there any question from the meeting room? We give some time for people online, maybe tapping and come up with some questions. And
while they are typing it, are there any questions from the audience sitting here?
Yeah. Very simple question. If we consider about multiple risks, it will be extremely hard for like all the engineers work together for the real projects.
Yes.
So I just wonder like that will be practical in the future.
Yeah, absolutely. Very relevant question. Thank you very much. So we need to develop those analysis and design approaches such that even the practicing engineers are able to use it. I'll just give you one example. Earlier, the seismic design courses were not as developed. Then also structures were being designed by the engineers just by using thumb rule that 10% of the total weight of the structure is applied in the horizontal directions, and they used to design. Of course, it was very conservative, highly conservative. As the technologies have developed, as the knowledge has developed, we are now having a very sophisticated course for designing earthquake resistance structures. But again, not all the structural engineers are fully familiar with earthquake resistance design as such. So there are very simplified approaches such as seismic coefficient method. Very simple. It is quasi-static approach of designing seismically resistant structures. On similar lines, we have to develop certain design procedures, design tools, such that even a common engineer, common structural designer will be able to use them without going into too much details of the technologies involved in different hazards and to cater for risk in different hazards. Yeah, so there is a long way to go to reach up to that level where every common engineer is able to take into account all the different risks from different sources.
Actually, that's a question about what's the main challenge for defense when you try to qualify slow fire compared with other impact hazards. in the experience learn from like the engineering other.
So far, our joint work has led us to think on the line that there is not a direct comparison between these hazards. So quantifying the vulnerability, quantifying how the structures perform against these kind of loadings, they are very, very different. You can have some small learning lessons from one hazard while we are assessing for the other hazards, but that is not useful. For every hazard, we need to look very separately. And typically, if we talk about fire hazard, there are so many considerations that we need to give. If I compare that with earthquake engineering, it is pretty much straightforward. Generally, it is only one intensity measure that suffices in quantifying the fragility or vulnerability. But that is not the case in case of fire.
Thanks so much.
Yeah. From the online audience, are there any questions?
It's about the bamboo fiber one. I mean,
Yeah.
I'm also curious, what's the performance compared with, let's say, carbon fiber or.
Yeah, so because carbon fiber is a artificial man-made material,
Yes.
bamboo fiber is naturally available. So the performance is significantly different because in the man-made material, it is up to us how we make the surface finish. So the surface finish in case of carbon fiber that we use is roughened, and thereby there is a very good bond between the carbon fiber reinforcement or glass fiber or any other fiber that we use and the surrounding concrete. But in case of bamboo, there is a very flimsy bond between the bamboo reinforcement and the surrounding concrete. There were some attempts made as to how we can improve the surface characteristics. For example, some of our students, they wound around that bamboo fiber some ropes so that there is a gripping, but that didn't help much. So the main failure mode in case of bamboo reinforcement is the delamination between bamboo and surrounding concrete, which is not necessarily the case in case of internal carbon fiber reinforcement. So that is in terms of bond behavior. In terms of strength, obviously again, one is the naturally developed material, but still we do call that as a functionally graded material, because if you see a single bamboo, then all the fibers are oriented only in the longitudinal direction, and it is having very good strength as such. But then because it is naturally available, we cannot guarantee that how much strength every bamboo has. So there is a lot of variation in terms of its material properties. When it comes to degradation, obviously bamboo is much more vulnerable to exposure to higher temperatures as compared to carbon or other such synthetic materials, as well as, of course, we need to worry about termite treatment also given to bamboo as compared to the carbon. So as such, a one-on-one comparison between carbon fiber reinforcement and bamboo reinforcement is rather not possible. Maybe if I can take that discussion forward, we are trying to see how we can engineer these kind of natural sources.
Yeah.
To engineer them for our purposes in built infrastructure. In some 2 or 3 slides, I talked about it. What kind of biocomposites we are trying to develop, not just from bamboo, but from the agro residues. So that is already an ongoing effort in our laboratory.
Yeah, because I thought like the way you apply bamboo fiber to concrete is kind of similar to like ways you apply carbon fiber to concrete as well.
Yeah.
So I thought you did lots of tests. So how about the structure performance, like compared with carbon fiber and concrete?
Yeah, so in this case, the full bond could not be developed. So you can see in most cases for the exposure to fire, it is the delamination failure that govern the response rather than failure of the bamboo niche. Of course, bamboo has started degrading after about 300 to 400 degrees Celsius. So you can see that these black spots are because of that higher temperature. And just before that, there was already spalling for the concrete. But when we expose the carbon fiber reinforced polymer panel to this temperature, typically it does not show this kind of spalling at this temperature level. And obviously, the material proper in terms of material properties, the epoxy is it oxidizes much earlier, but then fiber they do remain for some more time. But if you talk about the individual bamboo and individual carbon fiber, that comparison one can make. Individual bamboo fiber we are currently testing. Those tests are not complete, but individual carbon or basalt fibers we have tested already, and in one of the slides I have shown that. And there, so we have tested these basalt fibers and we have found how the tensile strength degrades with increasing temperature. So you can see that even up to about 400 degrees Celsius, there is almost no strength remain in the. These are for basalt fibers results naturally. Yeah. But we need to now have one more curve here on top of this format. But we don't have those results as of now. One of the challenges how to hold the bamboo in the grips, because when we try to load it in tension, there is slippage at the end. Yeah. And we cannot just tighten it because there will be localized failure at the grip level in the bamboo cones. And then even the sizing of the bamboo and what kind of specimen we should have, what kind of gauge length we should have, there are hardly any guidelines available. So that part is currently in process. So that one-on-one comparison between CFR to GFR or BFR to rods with respect to bamboo is not available right now with me. But from structural considerations, yes, we do have some leads on that part in terms of those panels which I have shown that we have. Was that your question? Yeah.
I actually have the one last question. It's like so there are some different structure design has better resilience performance than others.
Yes.
So when against, let's say, earthquake or something else.
Yes.
So did you find something?
Yes, we did.
For
And
fire safety
yes,
engineering?
yes. So during the talk, I said that because again, time is limited, I did not present those results here. But in some of our tests, we have tried to achieve the ductility through structural means rather than through the. Whenever we talk about ductility, inelastic deformation, we talk about the nonlinear curve for stress strain of material behavior. But when we talk about these synthetic fibers, or even for that matter, these organic fibers, the material behavior is just brittle. Right? We don't have any nonlinearity. But then we are not restricted to rely only on the ductility achieved through material route. Rather, we try to achieve the ductility through structural or system route. So we have put the brittle reinforcement here. Concrete is brittle, reinforcement is brittle, but we have adopted different ways of providing that reinforcement in the concrete structure. What are those different ways? One is layering of the reinforcement. So there is some reinforcement which is closer to the neutral axis, such that those layers which are extreme from the neutral axis, they are stretched to their limit and they fail in a brittle manner. Nonetheless, there are other layer which is yet to fail, but your load deformation diagram plot has already now shown a different stiffness. It has degraded. Right? So you get a pseudo ductility. So that is one way. Second way is we have pre-stressed them, and the level of pre-stressing was different, as well as some of the rebars, they were not pre-stressed. So they had some reserve capacity. So when some tendons fail, there is a reduction in the stiffness, and that happens in a progressive manner. So stiffness reduces gradually. So if you see the overall stress strain diagram, you will see that it has significant non-linearity, even when all the material used is brittle. Right? Likewise, we have also changed the grade of concrete and so on. There are different ways we try to achieve that ductility. So we could achieve that ductility not from the material route, but from the structure or stiffness route. So these are some of the ways that can be introduced to improve the performance, not necessarily from the conventional ways. Some innovative or novel ideas needs to be incorporated in order to meet some of these performance requirements, be it earthquake hazard or fire hazard or any other hazard for that.
Yes, very much.
Sure.
We handle around your time. Is there any last minute question from online or also from the room?
Anything, David, that we should fix?
Actually, it's on the this way, only have 2 minutes left. Yeah. Just wait for maybe 1 more minute.
Yeah.
For any last minute questions. And I mean, for the people in the room, we got some soft drink over here. After this, we can have some drink. And sorry for those people online, but you can buy one for yourself.
Yeah, next one is 6:30.
We kind of about finished because it's about the time. So, I mean, thanks again for your such a great presentation and your answer for my question. And thanks everyone attending from online, and thanks everyone attending over here. We'll see you on the next SFP seminars. Enjoy your night. Goodbye, everyone.